Hello, mathophiles. On this episode, we're going to actually prove that the general linear group is in fact a group. So, some professors often insist that you should not use the word group until after you prove something is a group, but I tend to be kind of carefree about that because we know it is. But it is worth pointing out, technically, you shouldn't say something is a group till after you show it. So, the goal is to prove that put our money where our mouth is and actually do this proof. As a reminder, the general linear group is the set of n by n matrices with non-zero determinant. In our case, n is 2, so we're talking about 2 by 2 matrices with non-zero determinant, and the determinant of a 2 by 2 matrix is the product of the diagonal entries minus the product of the anti-diagonal entries. And as a convention, we will, given a matrix A, we will write it in this format. In other words, we will use subscripts to refer to the entries of the matrix rather than individual variable names for each entry, so that the proofs are easier to write down. And in case you've never seen this notation described this way, the first index tells you what row you're in, and the second index tells you what column you're in. And the way I was always taught to remember this is to think of RC Cola. So hopefully you're not an alcoholic, because then you might be thinking of Crown Royale, and that will screw you up. So RC Cola, rows by columns. So how do you multiply two matrices? Well, A times B, the ijth entry, so the entry in the ith row in the jth column, is given by this complicated summation. So you take the ith row of the first matrix, the jth column of the second matrix, and for each entry in the ith row, you multiply by the corresponding entry in the jth column in the second matrix. So first entry in the first row times first entry in the first column, so on and so forth. Multiply them all together and add it up. And you might prefer, possibly, if you remember this notation, an alternative way to think about this in terms of dot products is if you write a matrix as a bunch of vectors. I guess we use column vectors. Then you're just taking the transpose matrix, the ith column vector, and the dot product with the jth column vector of the B matrix. Either formula works. So our claim is that 2 by 2 matrices with real entries and non-zero determinant form a group under multiplication. So let's prove it. So first we have to show associativity. So we remind ourselves what that means. So this is not part of the proof, it's just a thought bubble. For every 3 elements in the group, AB times C is equal to A times BC. So order parentheses doesn't matter. I should remark here, in case students are curious, that the choice of R here is to make our lives a little easier, but technically you could use C or Q, and the proof we're going to do works. It turns out if you work with integers, the proof doesn't quite work. If I recall correctly, you have to assume not that the determinant is non-zero, but that the determinant is either plus or minus 1. And the reason why is because our formulas for inverses of a matrix require us to be able to divide, and you can't always divide integers. But ignoring that digression, let's actually do this proof. So first we prove that multiplication is associative. Well, what do we need to do? We need to show a universal quantifier, so we take 3 arbitrary elements in this group. So we take 3 arbitrary matrices, and then we just need to check that this equality happens. One way to do that is to actually multiply these matrices out as matrices, and I've done that proof once before, and it gets very tedious very quickly because, well, the formulas get very ugly, so I will do it slightly differently, but it's the same idea. So instead I will use the formula that we just wrote down. So what is the ijth entry of this product? A times B times C. Well, it's this summation over all k, where you multiply the ith row of the first matrix times the jth row of the second matrix. And so this k says we go 1 and 2. Okay, that's a little vague, so I will just point out, our formula was that you sum on k. But in this case, n is 2, and so there's only 2 terms in the summation, and here they are. K is either 1 or k is equal to 2. Well, next we apply the definition of multiplication to a times b. So a times b, the I first entry of a times b is given by this formula. So what does this entry tell you? It's the entry in the ith row and first column. So these are the entries in the first column. And these are the entries in the second column. So we got AI1, B11, AI2, B21, AI1, B12, AI2, B22. One way you can always check that you didn't make a mistake is that the second coordinate of the first term is the first coordinate of the second term. That's the way this formula always works. So I do that check and I see that it's correct. And, well, I guess the only thing that makes sense at this point is to distribute this multiplication. And what do I get if I do that calculation? Well, I get a formula for the ijth entry of the product of these 3 matrices in terms of the entries of the individual matrices. In other words, I get this complicated expression. We notice it has 4 terms. Each term is a product of an entry from A, an entry from B, and an entry from C. In each case, the A entry starts with I, and the C entry ends with J. And you can see that the second coordinate of the A entry and the first coordinate of the B entry is always the same. And the second coordinate of the B entry and the first coordinate of the C entry is always the same. And since those values either are 1 or 2, there's 2 options each. And 2 times 2 is 4, and so we see that we get these 4 entries. So you see that in general, what we should expect to get should be something like AIK, BK, L, CL, J, where K goes from something to 1 to n, and L goes from 1 to n. If you follow this calculation out in general, you should get something like this. But in this particular case, the calculation's a little easier. It's just these specific 4 things. So far, we did this calculation where we computed the ijth entry of this triple product of matrices. And we got this complicated formula. If we want to prove associativity, what we want to prove is that the ijth entry of this matrix is equal to the ijth entry of the other matrix, which is the triple product where the parentheses is in the other order. So if we can prove that these 2 things are the same, regardless of what I and j are, then these are the same matrix. And then therefore, multiplication is associative. So let's do that calculation. Again, applying the definition of multiplication of matrices, we get that looking at the ith row of A, we get AI1 times the jth column of B times C, B dot C 1 comma J, ai2 times b dot c2 comma j. Then we apply the definition of matrix multiplication to p times c, and we get this expression. And then the only thing that makes sense is to distribute. And then at the end, we see that we get these four terms. Notice that there are some differences here. Namely, the middle two terms are in a different order. So we see that this first term is the same first term. The last term is the same last term. But this second term is the third term down here. And the third term up here is the second term down here. But since addition is commutative for real numbers, and these two expressions are in fact real numbers, that means that these two expressions are equal. So we actually do have that this first expression is equal to this expression. Also, it's worth pointing out that what we've actually done doing this calculation is we've gotten the sum on k, L, AI, K, BK, L, CLJ. In other words, if you actually do the calculations using the formulas with summation notation, you will see that you get this instead. And so the only difference from the previous formula we had before is this order of summation is different. But since summation is commutative, the order of summation doesn't matter. And so actually this associativity holds for arbitrary n by n matrices. But since this is often harder to look at, I find it's often easier to look at the 2 by 2 case, where the formulas are a little easier to write down. Except, as you can tell, I did it this way. It would have been a lot harder if I actually did it with the 2 by 2 matrices where I actually write down the all four entries, because can you imagine me writing down a 2 by 2 matrix where this is just the upper left-hand corner and then you have something in the upper right-hand corner? Yeah, it's a very big matrix. Which is pointing out a principle you learn in mathematics when you start to write proofs for yourself. Oftentimes you go through many drafts trying to figure out the simplest way to convey the idea. And so this is the simplest way to convey the idea that I know of currently. And so, actually continuing on with the proof itself, what have we shown? We've shown that the ijth entry of A times B times C is equal to the ijth entry of A times B times C. Let me actually add in the quantifiers, because I actually haven't been doing that. I would lose points on this proof because I should have mentioned what I and j were earlier. Since these two matrices have the same entries, they're the same matrix. And since A, B, and C were arbitrary matrices, multiplication is associative. And that ends the first part of the proof. So we took three arbitrary matrices and we proved that it didn't matter whether you multiplied the first two matrices and then multiplied by the third, or if you multiplied the second two matrices and then multiplied by the first. Now, continuing on with the proof, it's not enough to show associativity. We have to show that your group has a multiplicative identity, which means that there existed an E and G such that left multiplication by E is the identity function. Meaning if you multiply E by any other element, you get the other element back. We already did this calculation in the other video and discovered that the correct choice of E is the identity matrix. So that's what we're going to show. So since it's an existential quantifier, we get to pick the element and then show that it has the right property. So we say, now we show that our group has a multiplicative identity. Now I'm going to specify what it is. It's this special matrix. Now the only thing I have to do in the rest of the proof is to show this second statement. Now this second statement involves a universal quantifier. So I take an arbitrary matrix in my set, and then I need to do this calculation. So take an arbitrary matrix A, let A be in GL2, and then let's compute E times A. Well, by definition of matrix multiplication, here is the matrix. Well, let's see what happens. 0 times anything is 0. And 1 times anything is anything. Is the other number, because 1 is the multiplicative identity for the real numbers. And what do we get? Well, we get A11, A12, A21, A22. So it looks like we actually get A back again. So we've shown the thing we wanted to show, which is that if you multiply any matrix by E, you get the other matrix back again. So E is in fact the multiplicative identity, which is what we want to show. So our group has a multiplicative identity. Now I mentioned in the other video that once you found the multiplicative identity, actually showing it is one is an easy proof. And you see, this is much, much easier than the associativity proof. Of course, to aid the grader, we say hence E is the multiplicative identity of GL2R, so that the grader knows we've finished this part of the proof. Finally, we're at the last step in the proof. We need to show their inverses. So finally, we show that our group has inverses. What does that mean? It means that for every element in the group, we can find a multiplicative inverse, some element G inverse, such that this equation holds. We have a universal quantifier in our statement, so we should start with an arbitrary matrix. Given that arbitrary matrix, we need to find a new matrix that has this special property. So in our proof, we take an arbitrary matrix in our set, and we define a new matrix A inverse to be this thing. So we've swapped the diagonal entries and we negated the anti-diagonal entries, and we divided by the determinant. And you either knew this because of the formula you memorized in the linear algebra course, or because you watched the last video where we derived it from scratch, which is actually the more enlightening way to do it. The point is, we figured this out in advance. We knew the right formula. So now that we know the right formula, we pull it out of the hat. We say, this is the right thing, or at least we claim it is, and now we're actually going to show it. So we're going to check. So we've taken an arbitrary matrix. We've satisfied the existential statement. This is the only part left we need to show. Now we do the calculation. I realize I should probably put my grammar on here. These are actually still sentences, so sentences still start with words. It's actually considered improper to start a sentence with a mathematical symbol, so you should always start with a word. So I should start with a word like then. I shouldn't just start with A inverse. Okay, now that I've made that correction, then A inverse times A is, let's do the calculation. We had the 1 over A in front. Let's do the calculation. You do this matrix row times the first row of A, in case you want to actually do the calculation, because it is fun to do it at least once. It's worth reminding yourselves that this is what A looks like. First column of A. And so I'll underline that those were the entries from the first columns. The first column of A, the second column of A, first column of A, second column of A, and the other entries are the ones we're getting from the first row of A inverse, and the second row of A inverse. So with that in mind, you can see and check that this is the calculation we get for matrix multiplication. Okay. Looking at it, thinking, yes, it is correct, which is good to check. And now we look at it and we see some other patterns we might not have noticed before, namely A22, A12 minus A12, A22 is 0, and similarly down here. And what happens with the other entries? Well, this is just the determinant, and this is just the determinant of A. And actually, this is what I used to do on exams if I couldn't remember the formula for the inverse of a 2 by 2 determinant. If you don't remember exactly what it is, but you know it's something like this. Like, I think the most common thing I would forget is whether you negate the diagonal or the anti-diagonal. What I would do is I'd go to the margin, I'd do one of the two calculations, I'd do this calculation, and I'd see if I get the identity matrix or not. And if I got the identity matrix, then I had the right formula. If I did not, then I made the wrong choice. Which is a good argument for why proofs are sometimes useful, because you can use proofs to figure out whether or not the formula you think is correct actually is correct by verifying that it has the property it's supposed to have. Anyhow, we see that we get this calculation. But since you're scaling by 1 over the determinant of A, these are both just can be canceled and replaced with 1s, which is our identity matrix. And so we see that multiplying A inverse times A actually gives you the identity matrix. Please note this actually requires a proof, because technically I'm calling this A inverse because I'm trying to prove this is true, and this is technically a faux pas. Some professors actually insist that you should use a different name for this matrix until after you've finished this proof, because otherwise it looks like you're assuming the conclusion, which is a very bad thing to do in mathematics. But so what I like to say we're doing is that we're verifying that this actually is the correct formula, and we see that it is. And so we actually do have inverses, and this is the correct formula for the inverse. Once we include our remaining sentences, pointing out to the reader that we've finished this section of the proof, and then that we've finished the proof completely. So we have inverses, and we have a group. And so we are done with the proof. Why? Because we checked that we've satisfied all 3 group axioms. It is worth pointing out that it is best that each of these parts is a separate paragraph, and that you follow normal rules of grammar. It's worth pointing out that equal signs are considered verbs, so this is technically a sentence. Screw you, English teacher. I mean, mathematicians work by slightly different rules, but there you have it. I usually prefer calculations done in such a way that it's easy to follow. You'll see in other videos that I will do calculations step by step with explanations.